Assalamu alaikum, my name is Ayila Naeem and here is my lab report number 8 of DSP. The lab objective of this lab is to implementation and analysis of moving average filter and implementation and analysis of finite impulse response filter Fourier transform design method. In task 1, which is the defined filter, a filter in the context of DSP refers to a system or algorithm that modifies the characteristics of a digital signal. Filters are used to extract, enhance or suppress specific components of a signal based on their frequency, amplitude or phase properties. The second point is types of filters. Low pass filter, it allows frequency below the specific cutoff frequency to pass through, attenuates frequency above the cutoff frequency, and used for removing high frequency noise or extracting low frequency components. And second type is high pass filter, it allows the frequency above a specified cutoff frequency to pass through and attenuates frequency below the cutoff frequency and used for removing low frequency noise or extracting high frequency components. And type 3 is band pass filter, it passes a specific range of frequencies centered around a central frequency. It attenuates frequency outside the specific bandwidth and used for isolation specific frequency bands in signal. The fourth type is band stop filter, which is also called notch filter. It attenuates a specific frequency range of frequencies while allowing frequency outside the notch to pass through and used to remove interference or unwanted frequency components. And the last type is all pass filter. It passes all frequencies with equal gain but introduces a phase shift that varies with frequency, does not alter the amplitude of the input signal but affects its phase, and used for phase correction, creating delay effects or implementing phase equalization. What are the time domain parameters for a filter? The time domain parameter for a filter is a step response. It may be good, bad. The good is a good step response indicates that the filter settle quality or smoothly to its final steady state value without significant overshoot or oscillations. Bad is a poor step response may exhibit slow settling time, excessive overshoot, undershoot, or isolations. Um, This can result in signal distortion, inaccuracies in tracking input changes, and instability in the filter's behavior. For overshoot, um, point good. A low or negligible overshoot is desirable as it indicates that a filter output closely matches the desired response without signaling deviation or transist effect. And for bad point, excessive overshoot can lead to signal distortion, ringing, or instability in the filter's output. It may cause unwanted oscillations or introduce artifacts that affect the accuracy and reliability of the filter signal. In linear phase, the good point is linear phase is considered beneficial as it ensures that all the frequency components of the input signal experience the same phase shift, preserving the signal's waveform and avoiding phase distortion. This is particularly important in applications where phase coherence and signal fluidity are critical. Whereas the bad phase is that non-linear phase responses such as phase distortion or phase shifts that vary with frequency can lead to signal degradation, smearing of transist signals, and altered frequency characteristics. What are the frequency domain parameters for a filter? Which are roll off, ripple in pass band, and poor stop band attenuation. So in the task 2, plot a signal in time domain and frequency domain along with its magnitude response, and the source code is the source code is define the signal x, which is x is equals to zeros 1 1 and 1 to 40. In the second step, plot the signal in the time domain, and in the third step, compute the Fourier transform of the signal, which is x is equals to fast Fourier transform, and compute the magnitude response. Magnitude response is equals to absolute of x. Plot the magnitude response in the frequency domain. That is, subplot is 3, 1, 2, and give them title x label, y label, and plot the signal in the frequency domain. Fast Fourier transform plot. The output in the signal, the output of signal in time domain, magnitude response, and signal in frequency domain is given. While the second source code is when define the signal x when x is equals to zeros 1 and 120 and x is 41 ratio 120 is equals to 1. Plot the signal in the time domain. Compute the fast Fourier transform of the signal x is equals to fast Fourier transform of x, and compute the magnitude response, which is magnitude response is equals to absolute value of x. Plot the magnitude response in the frequency domain and plot the signal in the frequency domain. In code, the next code is define the signal x, which is x is equals to 0, 1 and 161, and the ratio of x is 41 to 120, which is equals to 1. Plot the signal in the time domain, compute the fast Fourier transform of the signal, compute the magnitude response, plot the magnitude response in the frequency domain, and plot the signal in the frequency domain. The output of the signal in time domain, magnitude response, and signal in frequency domain is given. Now the source code, when the ratio of x is 121 up to 161. So define the signal, which is x is equals to 0s 1 up to 161, and the ratio of x is 41 to 120, which is equals to 1. Add noise to x, which is x noise is equals to x plus 0.5 and random size x. Now plot the noisy signal in the time domain. Compute the Fourier transform of the noisy signal, compute the magnitude response of the noisy signal, and plot the magnitude response of the noisy signal in the frequency domain. And then plot the noisy response in the frequency domain, fast Fourier transform plot. And the output of noisy signal in the time domain, magnitude response of the noisy signal, and noisy signal in frequency domain is given. The next code is when x is equals to 0.5 random size of x. So define the signal x, add noise to x, define the moving average filter coefficients, and apply the moving average filter coefficient to x. Plot the filtered signal in the time domain. Now compute the Fourier transform of the filter signal, compute the magnitude response of the filter signal, and plot the magnitude response of the filter signal in the frequency domain. And at the end, plot the filter signal in the time domain, fast Fourier transform plot, and the filtered signal in time domain, magnitude response of filter signal, and filter signal in frequency domain is given. The next task is define the signal when x is equals to 0s 1 by 161 and the ratio of x is 41 up to 120. Add noise to x, define the moving average filter coefficients, apply the moving average filter to the x noise, plot the filter signal in the time domain, compute the Fourier transform of the filter signal, compute the magnitude response, plot the magnitude response of filter signal in the time domain, and plot the filter signal in the time domain, FFT plot. Filtered signal in time domain, magnitude response, and filtered signal in frequency domain are given below. This is also the same as the above, which gives the filter signal in time domain, magnitude response of the filter signal in frequency domain. In task 3, repeat example 7.2 up for 7 tap coefficients. Put the coefficient n is equals to 16. This is number of taps. F of c is equals to cutoff frequency in hertz, which is equals to 800, and sampling frequency is equals to 8000. Calculate the normalized cutoff frequency between 0 and 1. Now calculate the filtered coefficient using Fourier transform method and display the filtered coefficient. Determine the transfer function using the filtered coefficient and convert the transfer function to symbolic form to equalize equation multiplicator. Display the transfer function in symbolic form. Determine the difference equation using the filtered coefficients and display the difference equation. Now compute and plot the magnitude frequency response and mark the specific frequencies. So this is the filtered coefficient and transfer functions h of z, and then the difference equation is this. The magnitude frequency response graph is given. Now repeat example 7.2 up for 51 tap coefficients. So the number of taps is now 51 and the cutoff frequency is 800 and sampling frequency is 8000. Again, calculate the normalized cutoff frequency between 0 and 1 and calculate the filtered coefficients using the Fourier transform method. Display the filtered coefficients. Determine the frequency, determine the transfer function using the filter coefficients and convert the transfer function to symbolic form of equation manipulation. Display the transfer function in symbolic form. Determine the difference using the filtered coefficients and display the difference equation. The output of column 1 through column 13 is this. The output of column 14 through column 16 through column 26, and the output of column 26 through 39. The output of column 40 through 51 is this, and the transfer function of h of z is this, and the difference is given. The magnitude frequency response of the above code is this. Again, repeat the example up to 51 coefficients. The above procedure is same. Magnitude frequency response is given. We changes the number of coefficients, that is the number of tap coefficients. In part B, apply the filters made in part of a signal X signal. Observe the changes of the signal in time and frequency domain while varying the number of coefficients of the filter. So original signal generation is f of s, sampling frequency is 8000, the time is 0:1 frequency sampling, and x1 is equals to this, x2, x3, and calculate the whole signal by signal x is equals to x1 plus x2 plus x3. Now plot the signal in the time domain, plot signal in the frequency domain, and design and apply FIR filters with varying number of coefficients. Design FIR low filters and apply filter to signal x. Now plot filtered signal in the time domain, plot filtered signal in the frequency domain, and the resulting output is this. Original signal in time domain, original signal in frequency domain. The filtered signal in 17 coefficients in time domain, the filtered signal in 17 coefficients in frequency domain. In task number 4, repeat the example with 7 tap and 17 tap. So number of taps for the FIR filter is 17. The sampling frequency is 800, and the lower cutoff frequency is 2000, while the upper cutoff frequency is 2400. Normalize the frequencies in the Nyquist range. Calculate the bandpass filter coefficients using the FIR function 1. Display the filter coefficients. Determine the transfer function using the filter coefficients. Convert the transfer function to symbolic form of equation manipulations. Display the transfer function in symbolic form and display in the frequency response of the filter. Now plot the graph and the frequency response of the 17 tap FIR bandpass filter is this. In part B, apply the filters made in part of a signal X. Observe the changes for signal X in time and frequency domain while varying the number of coefficients of the filter. F of s is equals to, frequency sampling is equals to 8000, the time is to 0:1 divided by frequency sampling, and x1 signal is given. Now compute the whole signals by giving the name signal x is equals to x1 plus x2 plus x3, and plot the original signal in the time domain. Compute original signal in frequency domain and filter coefficients for 5 tap, 9 tap and 17 tap FIR bandpass filters. Apply the filter to the signal x. Plot filter in the time domain, plot filter in the frequency domain, and the output of the original signal in time domain and the frequency domain is given, and the filter signal with 5 tap FIR bandpass filter in time domain and with 5 tap FIR band filter in frequency domain. So thank you so much for watching my video.